Let's continue our discussion on shortest path algorithms, and especially Dijkstra today. And we will look at some of the visualizations. There's some tools to get some, because I think seeing things in action are more important. So let's see how we can visualize the solution, and then maybe we'll also see about coding a solution ourselves. So there's a couple links to the visualizations. One is perhaps, where's my other one? This one will look. This one is more general, right? We want to find algorithms, we want to Dijkstra, right? And visualize it. That's where our source, destination. So how is Dijkstra? So in this particular case, it's weighted and guarantees shortest path, right? So here, the weights are basically 1, right? There's no particular weight here, right? It's just, and it's, you can go both directions. So let's see how it works here. So Dijkstra is not going to be the best solution here, actually. Because notice what's happened here, right? So to find solution from here to here, right, it had to go through all these different possibilities, right, until it reached here, because it had to explore the solution space. So it had no knowledge, okay, that this is actually the best way to go. So next week, not next week, this week, next lecture, we'll look at some improvements to Dijkstra when we have some hints, right? But for now, you can see that Dijkstra is not maybe, you spend some time going around. If you have two-dimensional space and you have some hints, maybe you can do better. But okay. But we'll look at here how the other one at the US FCA is a pretty nice tool, right? So we have some graph, and this is our visual or logical representation of graph. Hopefully you can see this, right? I don't know how visible is it. It's pretty easy to see. Yeah. Oh, pretty good actually. Okay. So it's a directed graph. Of course, you can do also undirected. It doesn't really change here, right? But notice something here, logical representation, not just visualization. But we have basically, we have a couple ways of choosing how do we represent our data, right? Meaning vertices and edges. So one way to do is adjacency list, right? You have 0, and you say, okay, to 2 it costs 4, to 3 it costs 9, 4 costs 7. Is that correct? Let's double check. Yes. To 2, where is 2? No. Let's see here. From, let's see. 0, 2, from 0, 2 is 4. That doesn't make sense. Where is my 2? Oh, yeah, it's correct. Yeah, from 0, 2 is 4. How about 2? 4 is 7. Yeah, and 3 is 9. And that's it, right? So for each vertex, you add this little list of values. Again, it's good for sparse graphs, right? If you have only a few edges, this is a good representation to use, meaning how to store the data. If you have a full graph, right, getting close to complete graph, right, then this adjacency matrix would be more suitable. So here notice, so from 0 to 2 is 4, from 2 to 0 is nothing, right? It's not symmetrical, right? Right, because, it's not both ways, right? Except here, like 3 to 5 is 2 and 5 to 3 is 2. So this is symmetrical. Let's double check what's the case here. Yeah, 3 to 5, you have arrows both ways. So this would be a case, if this is undirected graph, it'd be like basically just like this. This is one case where it's exactly like undirected graph. Both ways cost same, right? Okay, but so let's see this in action. So which vertex are we going to start? I guess we'll start with 0, right? So what's going to be known about so how are we going, I'm going to pause, right? So how are we going to do it? We're basically going to feel that we don't know anything yet. The only thing we know that cost from 0, vertex 0 is 0 actually, right? What I don't like about this visualization, that the vertices are also numerical. It'd be better to use letters because they kind of a little bit distract from the numbers, right? Because vertex should probably be some names or something, right? City 0 or something. Okay, so run Dijkstra. So yeah, infinity. But notice something else interesting. So think about how do you preserve the path. Going back to our another slides here, right? So remember our shortest path, right? From S to V, it goes through T, right? Like I was checking actually also here, right? Google Maps, Riga Liepaja. Oh, this is actually, where's my Google Maps? Yeah. What happened to my path? Oh, come on, Riga Liepaja. Right. yeah, with a car, right? Atiet tagad, what the heck? Come on, Riga. Riga. Okay, you see, yeah. So, it is indeed goes through Skrunda or Saldus, right? You know, Tukums or, well, it contains, this is the shortest one, right? So, again, it goes through Saldus. This means that the shortest path, we also know the shortest path through Saldus. Again, why? Because if this Riga Saldus was not the shortest path, then therefore it would break also the longest path, shortest path for the full solution, right? So, this again, that's why the greedy approach works, because each sub-solution, right, Babite and so on, right, what's here, I don't know, there's nothing good here, right, right, so, no big cities, right, but each subsection will be the shortest path, by definition, right, otherwise, if it is not the shortest path, you could improve it, and therefore you would improve the full solution, right, so, again, so that's why it works. Now, so let's see this again. So infinity. So which one are we gonna? Okay, so let's do one more step forward, right? So yeah, so, but I was talking about this -1. What does that represent here? Well, we want to find the path. Now, if we go through here, right, do we need to know from Riga to Liepaja, do we actually need to know, like if you're storing this path, well, we have all these sub-problems basically. So we don't need to store full solution from Riga Liepaja, but instead we have solutions for each city. So where to go next basically, right? That's all we need. So we are saving a lot of memory, because imagine if you have a full map, right, to all cities, to Ventspils, to Daugavpils, you know, and Valmiera and so on, right? We don't want to store full paths. We just store enough, just information for Babite, basically, right? And then Babite has the information for whatever, you know, I don't know, what's, I guess, Durbe or something, or Zaldus, right? And so on, right? So we only need to know where to go next. So here, actually, it's doing this. It's saying where to come from, basically. So -1 says we don't know the path right now. So we'll use that to store the path. So let's take a look. So we start with 0. So what are we going to do? We are going by adjacency list here, right? We're going to fill out these 3 cities, right? These 3 vertices, right? So 2, 4, and 3, right? 9. So 2 is 4, 3 is 9, and 4 is 7. Let's take a look. Right, so we know T means we mark that we have visited, and here it's going to be infinity is more than 0 plus 4. We add it. Infinity is more than 0 plus 5. Yes, we added 0.7, and we are done for this particular vertex, which is a starting one. So which one are you going to pick next? Which one? First one, we don't have any connection at all. It's infinity.
Oh, so the second one.
Second one, 4, right? Because we know that's so we are guaranteed. We already know from 0 to 2. We already know the solution, right? That's why we pick it, because we already have solved it. So we pick this exactly, and so we say to get to 2, right? You have to go from 0, right? Which is obviously the solution currently, right? So that's where you come from. You have to go from 0, which just kind of makes sense, right? So now, okay, we mark it, you know, solved, right? True, like a bit flag, bit field, and let's add it. So now we do 2 to 6, right? 4 plus 9 is less than infinity. So we add it, and we have, that's it. Rest are infinity, we're done. So now we have 9, 7, 13, so we'll check what's 7, which is easy, right? There's nothing to do here, no more, it's dead end, right? And that's it. Now next one we'll check 3, and 3 will be a little bit interesting. We'll have 5, right? Let's take a look. And of course, we mark it solved again. And we are going to go to 5, right? Yeah, 9 plus 2, that's less than infinity, that's 11. Now we have 11, 13, and 2 infinities. So we of course will check 11, which is 5 here, right? Okay, excellent. All right. So let's take a look. On. We mark it solved. We check 1. Again, 11 plus 2 is less than infinity, so we mark it 0. 3 we already know, we don't go back, right? And now 13 is not more than 11 plus 2, so in this particular case it's a tie break, right? It's either way. We could of course add some extra structure to solve alternate solutions, like Google Maps does, right? But here we just, we don't ignore it in this particular case. So it still stays 13, and 7 we don't know yet. So we pick one of them, right? So 1 or 6. Let's do 1, right? And there's nothing, no improvement, because 2, going 1, this big jumps, 2 is, not useful. If this is 40, of course, it would be improvement, but we only have a nice short way, so no improvement, right? 2 is known, and it's also marked, right? So 5 is known, so 6. 13, this big way, 13 plus 8 obviously is less than 30, is more than 13, so we don't do anything, and we're done. So finally we have 6, and that's again, we're going to mark it done, and we mark 7, of course, with 20, because that's less than infinity, and we are done. We only have to mark it formally here, and that's it. Okay, and now the whole point is we can reconstruct the past. If it's -1, of course, here it's, we start with 0, that's the main one. How about 1? To get to 1, well, to get to 1, we need to go back. So 1 goes to 5, right? So we had 5, you see. Then we had 3, because 5 goes to 3, and 3 goes through 0. So this is a full pass. This is how we can reconstruct the pass, right? So by just knowing where we came from, we can reconstruct the pass, right? Does this make sense?
Yes.
Okay, very good. Okay. All right. So if I made you write Dijkstra without ChatGPT, would you do it? Would you able to do it? Not yet.
Well, maybe.
Maybe. It's not so hard. It's not so hard. Possibly. Okay. Now, so again, it will reconstruct all the passes, right? So by going through the previously known, these are of course trivial, 0, because it's 0 from the source. How about 5, right? We know it comes from 3. And of course 3 comes from 0, right? So 0, 3, 5. How about 6? 6 comes from 5. So 6 comes from 2, sorry. 6 comes from 2, right? And of course then it comes from 0. So I guess 7 is the longest one, I guess, right? So 7 comes from 6. 6 comes from 5, I believe. Yeah, no, from 2, sorry. From 2, and then it comes from 0, right? So using just a single entry, we can reconstruct the full pass. So that's kind of nice, neat little thing. So we don't, basically, again, in those days when memory was, expensive, we wouldn't want to, we didn't want to waste it, basically. Okay. So that's how we would solve it. But let's see if we can do this actually ourselves, right? That's a bit slightly trickier. And I'm going to go, I have already opened up a notebook. I think it's in here. Where is my, I'll open up code space in a moment. Where's my, oh, here we go, right, there we go. You can open up here in Colab if you want, right? In Python and NetworkX, right? So the good news, of course, again, would you be needing to use Dijkstra from scratch? Most likely not, because of course most good languages have a library implementation of this algorithm, right? So, efficient one. So let's take a look at this. How we solve it. Maybe you can see also how we could do it from a library. Now, I need code spaces, right? I need code space. Where's my code space? What do I have? Oh no, not there. What's? Oh, there we go. Right. Let's open up. So we'll go topics on Dijkstra, or shortest path, I guess. There we go. All right. So we have assumed this graph, right? And we want to go from, well, it should be from any vertex to all the other vertices, right? So let's do a kernel. Let's select kernel. Yeah, I'll do that. Okay. So again, we'll need some infinity, something to represent an infinity. Again, one way to do is system max size. This is what 2 to the 64 minus 1, I believe, right? Indeed, this is so this max size is 263, right? Yeah, okay. Indeed. Okay, so let's do this. So we have int max. Now this was originally from somebody else, so I think we'll need to do some improvement. Again, so how are we gonna, we probably first need a graph, right? And we could use, we decide how are we gonna store this information, right? So here, right, if you look at this solution space, right, adjacency matrix, like something like this. Well, we could do infinity, or we could do 0, minus 1. Let's see. When we supply initialization, it looks like it sets 0 for column range and for row in vertices, right? And also we save pass, right? All the vertices have -1. So that's fine. But only thing about this one here, 0. I'm not sure if it shouldn't be integer max actually here. Let's take a look. Minimum. And if you initialize, this is a diagonal, or maybe -1, perhaps. I see it. It's basically we set 0 for everything, right? We have 7 vertices, right? We'll need to, of course, add some distance, right? So this is going to solve the solution, right? We will also need find current minimum distance, right? And for search, not the nearest vertex, not in the shortest path tree, right? So again, and print path, print solution from source to destination.
Can you zoom in a little bit?
Yeah, I'll zoom in a little bit, right? Yeah, a little better. No, wait, control plus. One more. Yeah, I'll don't need this one. Yeah. All right. On print path, these are just utility functions, right? And this is the actual Dijkstra, right? So everything's infinity, right? Remember, 0, that's exception. Original is actually 0, right? And then this means and this is a set. In this case, well, again, in this particular here, instead of set, we are using a list, right? Again, not the most optimal. This is not the most optimal solution by any means, right? And then basically we go through all the vertices, right? We need to find the one which is closest, right? And again, we of course know that this one here is going to be the closest, right? And we set it true, right? We have visited, right? It's actually there, right? Instead of false, right? We set true, right? And then we need to update all the neighbors, right? Update all the neighbors of the one current vertex we are checking, basically. And that's it, right? And then we keep going again. So keep finding the next closest, and again update neighbors. Right? Next closest, update neighbors, and we're done. Simple algorithm, right? The only thing here is, again, it's of course implementation might be tricky, right? So for range here, right, we check, right, again whether we have an improvement, and then we print the solution. And again, so in this particular case, we supply the solution like this here, right? We initialize the graph, right? Graph 9, and we basically, this is not a great example because we are sort of, not great object-oriented programming. We supply the vertices and we have to initialize the graph itself, right? So this is going to be representing Which one? This particular here, right? 0 to 1 is 4, right? 0 to 1 is 4, right? And 1 to 0 is also 4. I guess so. Is this not? It's not directed, right? Yeah, this is not directed, right? Because that's why we mean it's symmetrical, right? We can go back, right? In this particular case, it's not going to make much difference. Well, cost to 7, 6 is 1. 6 to 1 is also 1, right? So let's find out all the shortest paths from 0 to all the rest. So let me run this code. Let's see if we can do this. All right, so distance from source is 0 up to 4 is 21, right? That's the longest, right? 21 is long. That's the case. Let's double check. Yeah, that's the longest. So 21. Which path would that be? 4, 8, that's 12, 19, 28. No, that looks bad. Let's see. 4, 8. Which would be the shortest one? I'm trying to see. Could we find it by ourselves? I don't know. Maybe this here. Yeah, I think this one. 0, 7, 1, 2, 10. That's 21. That looks like the case, right? Okay. All right. Maybe we need to, this graph. I'm not 100% sure. This solution was somebody else which I adjusted. Yeah, this guy here, and I don't really particularly like it too much. But it works. It works, right? Again, it all depends how we are going to solve, how are we going to store the graph, right? We're going to be providing vertices, right? And maybe we can also provide of course we also provide edges, right? So we can solve a smaller one, of course, right? It works. Okay, yeah. Well, we have time. We will look at the NetworkX solution, right? So NetworkX is a network library, right? So let's try importing NetworkX. Try. Yeah. Accept. Print. Install it. Install it. Yeah. All right. Let's try it. Okay. So let's do installation. Reminder that this is command line, right? Basically, exclam, right? So basically running system command. So 3.42. It's pretty well known for graph algorithms. Pretty nice library. Let me add this here. A little link. NetworkX library, right? NetworkX is a well-known graph algorithms library in Python. Right? Documentation. Yeah, let's see. Stable. Let's see. Oh, it's on GitHub now. They used to be outside GitHub. Yeah, for complex networks, right? Creation, manipulation, study of complex algorithms, right? So basically, right? Okay. So pretty much anybody who deals with graphs could use this library. 3.42. Oh, came out just like maybe last week. Actually, newest version came out. Right? Pretty good. All right, let's install. So we already installed this, right? All right. Could we add a hot link to this library? Maybe not. Now, so we installed it. Now we can try again, right? And now it should work. So we install. Let's get a graph, right? All right. Now I am going to also install Matplotlib for visualization. For visualization of Matplotlib, it's not maybe the best. We can use Matplotlib. Yeah, we'll use that for drawing, right? Because we want to do this. So let's start with a pretty well-known graph. This one here, right? So it's called Peterson graph, right? Slightly evil, right? But yeah, pentagram inside, right? But so Julius Peterson, 1898, right? Basically, it's undirected graph. It has some interesting properties, right? It's not, of course, complete, right? But yeah, it's like it proves some worst case scenarios. Basically, all vertices need at least 2 jumps to go to any other vertex, right? Vertex, right? That's some interesting, like, so you cannot go from in 3 jumps, right? So everything is connected, but at least at most 2 jumps, right? So it's called diameter 2, or actually radius 2, right? Radius 2, right? So shortest path. So in this particular case, if you have no weights, right? It will be either 1 or 2 for all the vertices, right? So 15 edges, right? Kind of cool graph. So since it's kind of well known, or this library NX, right, provides this, right? So let's take a look. So we're going to initialize it. We will initialize the graph with this Peterson graph. Peterson graph, which is a well-known graph in graph theory, exactly. And let's plot it, right? It's not going to look very nice, right? Yeah, we're going to plot. There's different ways of plotting. It's actually a big research field of how to plot things very nicely. So this is basically, you can see, unfortunately, it doesn't show a nice little star shape. How this one, where is it? Here, right? It would be nice to plot like this, right? We can't, of course, do it from here, right? Could we try it? Right? But let's go back to our graph, right? So we need to initialize, and then we need to add edges, basically, right? So in this case, we add all 0, 1, 4, right? Weighted edges, right? 0, 1. So these initialize where we start with, right? And where we go to, right? The question is now, do we need numbers? Or could we use letters, for example? Let's try this in a moment, right? So let's solve it. So get edge attributes, right? Let's print it. Yeah, it's kind of ugly looking. Still ugly looking. So layout's kind of bad. But maybe we could get we can get maybe the solution to this vertex cost, right? So we can solve it. Let's solving it with Dijkstra. Solving NetworkX graph with Dijkstra. Built-in Dijkstra. Yeah. Basically, you get out. We supply graph on the source node. We get the length and path, right? Length will be dictionary, right? Something like this. Solution, basically, right? How about path? Right. Length is a dictionary of, right, for the source node, which is 0 in this case, right? I'm curious if you could do letters. I think you can. How about path? How about path? How about path? Yeah. Path is actually also, what is it? What kind of data structure is this? What is this? What does it look like? It's dictionary, yeah. It's kind of, in this case, it could have been a list because, of course, the names are 0, 1, 2, 3. But, of course, it is actually a list, actually. So it's a dictionary with values as lists, right? Which makes sense. Okay. Again, so I'll use pandas for using pandas store results, right? We'll use that. And, of course, which is a pandas is a data analysis, is a post-data manipulation library, right? With NumPy underneath, right? And it should be included. Yeah, no, it's not included in this. Oh, okay, so we'll need to install it here. All right. Try importing pandas. And I need, of course, pandas is a great library. there are many options to install pandas actually. Okay, so I'll need to install it, I guess. All right, so we can install pandas, and yeah, there's lots of extra options. But let's see if we can live with this one for now. Yeah. NumPy is already included, date utilities, right, some things. All right, still installing. Because if you're running on Colab, you of course you already have pandas, you have everything already. I think you have even NetworkX already, I think. All right, 11 seconds, let's try it again. And it works. Okay, so we have nice little solutions and vertex and cost, right? So OG cost, right? We can compare it, right? Yeah, we have different numbering here actually. It's the same one, but we have different vertices. They're all mismatch. It's the same solution, but they're right. But we could sort it, right, and then we could check, right, if it's the same solution. Yeah, but this of course is now. Yeah, now it's okay. Vertex, yeah, cost. Okay, so all right. Now we have it solved. Yeah, now we have it solved. All right. But this is just basically extra. So now let's. Yeah, actually I've done it. So let's do this. Let's do better, right? This original solution of Dijkstra used the matrix, right? If you want to do better, if you use something called the priority queue, right? Meaning it's a queue, right? Which keeps, also has some sort of priority cost, right? Of course, here the priority will be the distance, right? So it's a nice structure, and the good news for you is, of course, we can use a heap queue, right? It's built in Python, right? So let's see what we're going to use, right? Graph, everything stays the same except we have heap somewhere here. Where's our heap? Fast reverse. Oh yeah, heap push. Okay, that's a big difference. Right? So difference. This is log v operation, right? Instead of doing a linear, right? We have a log v operation, right? And popping also is a log v, operation. So more efficient. That's how you get this. If you look at the complexity, there's a complexity. There's complexity here, right? Yeah. So this part here, that's where the log v part comes out of the heap of the priority queue. Right. Now we still inside of course we still have to go through all the vertices, right? And basically update. Again, this part here I would like to make this solution maybe a little more. Still needs some improvement, basically, right? I don't really like this way of adding. Well, I guess this is okay. I guess. Let's take a look. Let's initialize this class, and let's take a solve this. Yeah, it works already. We can print pass as well, right? Yeah, we can print pass. From 0 to 2, well, 0, 1, 2, right? Let's do the full solution. And again, from 0 to 4, let's see what the solution is actually. It's going to be 07654. Let's see if actually that's the case in real life, if this is actually the solution. Let's go back to our start. 07654, right? Yeah, it is. Okay. Outline. Optimize, yeah, right. 07654. So it works. But let's see, can we improve? Maybe we have like 5 minutes. Could we do any more improvements to this code? What would we like to see? So we have class, right? It's heap. So when it initializes, it has this vertical 0 because we don't use it at all. Basically, right? Could we use something else? I guess for this, we still use this adjacency graph, basically, right? So parent, so self parent. So what is this? Oh yeah, so that's where we go from, right? So parent is going to be the past. Yeah. So we will use a list to keep track of parent to represent the path where we came from, right? We initialize originally everything is infinity, all distances are infinity, right? Priority Q, PQ, or do we actually set it here? Where is our PQ? PQ. Self PQ. We supply PQ basically. Yeah, so we supply a list basically, right? We are going to be supplying this. We will be supplying a list to heap Q, right? So heap Q will take care of the rest, right? So we don't have to worry about this heap. Okay, maybe we'll have in that structures we'll have discussion how heap actually works. It's kind of cool structure. For now, it's fine. So set again more efficient to use set than list. Right? So some improvements. Now solution. What I would like to see maybe. So this is vertices. Maybe we can supply the graph here, right? Yeah. Graph is none, right? Yeah. If graph is none, else we do this, right? We supply 0, but of course, I don't know if you actually need this. Actually, this is kind of useless, right? Otherwise, we initialize the graph, right? 0 for column in range, for row in 0 for column range vertices. So we do everything 0, right? And we have an empty graph. Yeah, is nothing. Maybe we should basically do all infinity actually, right? Would make sense. Would make more sense to use infinity, right? Right. Yeah, where is our infinity, right? Sysmax size. Yeah. Yeah. And of course, since I'm lazy, right? Yeah. Control Z. Pseudo constant. I call them pseudo constant, of course, because of course should be 9 sine infinity, right? So 622 minus 1, I think, right? All right. Now, let's see here, right? So infinity, right? Yeah, because empty graph, all infinities, right? Yeah. So this is of course possibility again. So to do think about adjacency list representation, right? Yeah. So parent, right? This will be, of course, this makes sense to have a list, right? Vertices, right? Again, originally we have no direction. All right. Print solution, of course, simple. So mean distance, so helper function. This is a helper function, right here. Yeah. Helper function, yeah, with minimum set of vertices, right? So we supply the set, we find the distance, right? So we find the minimum distance here, right? The question is now, aren't we using here heap pop, right? So we don't need it actually here, right? Do we need, mean distance is not actually used here because we're using heap pop, which is going to work here, right? Yeah, because we supply this part here, so we don't need it here, right? We don't need this, right? It will still work, I hope. Right. Heap will take care. The distance, we don't really need here, right? Yeah. How much, right? Well, we can do verbose here. Let's do this. Let's do verbose option. Let's add a verbose option. Verbose false, right? If verbose, yeah, distance, okay. Current, yeah, and I'll do this here. Added to visited. Yeah, okay. So now we can also explore the solution, right? We have this little flag, basically, right? I can check what's happening to see this, visualize this. Okay, let's do this. And let's do a simple graph. And let's do verbose, right? Verbose is true, and see what happened. Yeah, so 0, 4, distance 4, you know, vertex 1 and vertex 2, right? And so we can also do graph here, right? And verbose true. You can see how it worked from 0 to 4, 8, 9. So here, these were the vertices, right? Maybe let me update this a little bit, and then we can take a break. So vertex, right? Right. Yeah. Okay. That should do it. We'll do it. Write this. Yeah. So 0, 1, 7, 6, 5, 4, 2, 8. Why did do it twice? I wonder. Right, because that's interesting. So 0, 0, 1. We checked twice, but didn't actually check up. Why did it pop twice? We popped. That's interesting, actually. Why did it do it twice? Doesn't seem to make. It shouldn't do it twice, right? We added while self PQ, while there's something to do. We push, right? We pop. Oh, we add them back. Right, we add them back. Okay, yeah, it makes sense, of course, right? We add them back here, right? It makes them, because some of them, so 0, 1, 8, 8, we had an improvement basically here, right? So distance 14, distance 14. Let's see again. So to 8, it's 14. So this is kind of weird. This is a little bit weird here, right? Why did it go from distance 3 is 19? Why is these two ones here? Basically, these two seem like unnecessary. They should not be popping out, right? So everything is correct, but these two are actually should not have been. For some reason, it seems like it's added back, right, to the push, right? Maybe there's an if statement which needs to be fixed. Try to check. We'll double check. If everything works, to do check why we get double. We did double. We have a few duplicate entries. So that's something not completely 100% sure in verbose printout mode. Okay, but otherwise everything works, right? And maybe there's something there shouldn't be pushing back. Yeah, parent. Oh yeah, no, this makes sense, right? So we put it back basically, right? We have improvement, we put it back, right? All right. Okay. So that concludes our lecture on algorithms. Let's continue at 11:15. Okay. We'll have more people.